Bismillahirrahmanirrahim. Today we will be talking about the statistical description of macroscopic systems. This lecture is from the course outline of Statistical Mechanics, having the course code of PHY231. In today's lecture, we will basically try to understand the different steps for the statistical description of a systems. We need to discuss each of the step in detail, and the other objective of this lecture is to understand the state of any particular system, specifically a statistical system, and at the end we will do the probability calculation, which is also a part of the statistical descriptions of a systems. There are 4 steps that are necessary for a statistical description of a systems, and these 4 steps are listed here. The first step is to specify the state of any particular system, that is called as a specifying the macrostate of a systems. This is the first step, understanding. The second one is choose a statistical ensemble. You need to consider assembly of particle and then consider that particular ensemble for that. So that is the second steps in statistical description of a systems. And the third step is the using the postulate of a priori probabilities. That is the basic concept or basic postulate of probability. According to this postulate, if there is any event to occur or any possibility or likelihood of any particular event, then all the possibilities are equally probable. Or in simple words, you can say that the probability of that particular events for all the possible cases is equal to each other. And at the end of this lesson, we will also do the probability calculation, that how the calculation leads us to a particular value, that is the probability of any particular systems. So let's come to the specifying the state of any particular macrostates. We already know the concept of microstate and macrostates. Macrostate normally describe the macroscopic systems or the macroscopic description of any particular systems. But when we are coming toward the microstate, we need to have detail much more information about that particular configuration of a systems. So in some cases, and in normal cases, there are many microstates that are possible in any particular macrostates. As this is actually not the part of in microstate and macrostate we will specifically discuss in detail, and we already discussed this in detail in the physical lectures. But anyhow, there are different microstates that corresponds to any particular macrostates. The macrostates is for any particular macroscopic system is a specification of the system macroscopic parameters. The specification of the system is just like when we are discussing the detailed information about that particular system, or in other words you can say that which particle is at which place, or which particle has been assigned that particular energy level, and if we are moving toward our understanding the nature of each particle involved in that system, so that is actually the specification of the microstate of that particular system. Or in simple understanding, the macrostate is the microscopic system stage. So if we look toward the quantum number for that particular case, a quantum description of the systems, this actually means specifying a large number of particles. So that is actually the set of quantum numbers. So if we have the classical description of the system, so this means specifying a point in large dimensional phase space. We already know the phase space, that is actually the position momentum space for any particular systems. So quantum description of the system, how we can quantum mechanically, or what is actually the quantum description of any particular systems. So if we are considering an isolated system, so this means specifying a subset of the quantum states of that particular systems. So this system is described by macroscopic parameters that can be measured. So that macroscopic parameter we can measure with them, just like if we consider a gas. So the pressure of a gas is a macroscopic parameter of that particular system, and we can easily measure the pressure of that gas. Similarly, the volume of that gas is also macroscopically measurable parameter of these systems. And so the second step in understanding of or treating any particular system is the statistical ensemble. In statistical ensemble, basically we need to decide exactly which ensemble to use. This is also discussed in this chapter in very details, and in this today lecture as well. So we have if we have classical mechanics or quantum mechanics, and we have a detailed knowledge of all the position and moment of all these systems particles, and if we knew all enter particles forces, we could in principle set up and solve the couple non-linear differential equation of motion, and we could exactly find the behavior of all the particle for all time in that particular systems. So in that way we can have a classical description or quantum mechanical description of that particular systems. So we also need this is actually the basics of statistical ensemble of any particular systems. So normally if we could set up and solve the couple or non-linear differential equation of motion, we could in principle find exactly the behavior of all the particle for all times. So in practice we do not have enough information to do this. Even if we did such problem is impractical and if not possible to solve. Instead we will use statistical or probabilistic method. That is why when we are treating the ensemble, we must have a statistical approach for that, because the 4 steps what we had discussed in the very detail of this lecture, that is actually the first slide of this second slide of this lecture, is that we are treating a systems statistically. Therefore statistical approach should be used for that, and the concept of statistical mechanics should also be involved in that. So when we are considering a statistical ensemble, we need to apply a statistical approach for that. So that is why statistical approach is basically the probabilistic method, because the particles are tiny and the particles are quantum, and we don't know exactly the position and momentum of that particle. What we have and what we can conclude is the only probability of its existence. So when the probability increases, so there are more chances or more likelihood of the presence of that particle. When the probability reduces, so the chances for the existence of that particle or that event reduces. So that is why this is a type of probabilistic approach, because we are not exactly sure about the position and momentum or other property of that particular systems or statistical ensemble. So that is actually the statistical or probabilistic method required for choosing an ensemble for that particular case. So we have some example for that particular case. We need we consider, let's think of doing many and number of particles that has similar experiments on the system of particles we are considering. So in general the outcome of each experiment will be different, and if we ask for the probability of a particle outcome, this probability is the fraction of classes and the fraction of cases out of an experiment which have that particular outcome. So this is how probability is determined by experiment. So that is a goal of statistical mechanics, is to predict this probability theoretically. So what we do, we need to calculate the probability theoretically, because we normally have a theoretical approach for that, and that theoretical calculation should be based on some particular justifications, and that is actually the fourth step or the last steps of the statistical treatment or statistical understanding of any particular systems. So the third step what we need to follow, or what is important to us when we statistically treat a systems or understand that particular system, and then consider that particular statistical ensemble. The third step for that is the basic postulate about the probability. That is a postulate about a priori probabilities. If we look at the a priori meaning of that, so prior is and its meaning is based on our prior knowledge of that particular systems. So our knowledge of a given physical system leads us to expect that there is nothing in the law of mechanics, which may be classical or quantum, which would result in the systems preferring to be in a particular one of its accessible microstates. So we need to utilize the concept of probability, that is the basic postulate of probability, to solve or to calculate the probability of that systems. For that purpose we need to find out all the accessible states. Accessible states actually mean the microstates. If we consider is every time I had given you some example of a 40 students, that is something about student, but keep in mind students are not a quantum particle, but that is a very simple examples. Just like we have 40 seats in the room and we have 40 students, so how we can arrange? So there are different ways of arranging the same student in the room. So say for example, if we can arrange the student based on their roll number, or I mean their this is one of the microstate. If we can arrange the student or allow the student to sit based on their names, that is in alphabetic order maybe, so that is one of the another possible microstate. So many microstates are possible for this description. In the same way, if we have 40 particles and 40 energy levels, so we can allocate the energy levels or the states to the particle based on different priorities. Say for example, we can allocate the position to the particles based on their energy, their position, their momentum, or their nature, so that there are various sort of microstates possible. So actually we need to calculate all the accessible states for that particular system, and all these accessible states are the microstates of that particular systems. Once we find all the accessible states, we can apply the third steps of the statistical mechanics and a statistical description of a system, that is regarding the basic postulate of probability. So that actually says that all accessible states are equally probable, or in a very simple words, all microstates are equally probable. Or we can also say that the probability of all microstates is same to each other. So if we look toward the definition of a priori in the dictionary, so it has various meaning, but anyhow its close meaning is like it means as a deductive, as relating to or derived from by reasoning from self-evident proposition. So that is presupposed by experiments, and that is being without examination or analysis, that is presumptive, and it is formed by conceived beforehand. So this is something about the a priori probability, but anyhow the simple understanding of the basic postulate of a priori probability is that the probability of all accessible states is equal to each other, or what we can say about this, that all the accessible states are equally probable. So that is actually the basic postulate of probability. Is also repeated here, that there is nothing in the laws of mechanics, that is might be quantum or classical, which would result in the systems preferring to be in any particular one of its accessible microstates. So that is something about the basic postulate of probability. Coming toward the further definition or understanding of the probability, if we have no contrary experimental evidence, we make the hypothesis that it is equally probable or equally likely to be probable that the system is in any one of its accessible states. This is actually the definition, basic definition or understanding of the probability postulate, that it is all the states are equally probable, or in very simple words you can say that the system is in any one of its accessible microstates is equally probable, or the chances of any particular events, I mean all the particular possible events in the of that particular are equally probable in that particular case. So let's come toward the hypothesis. I mean the hypothesis is that it is equally probable or equally likely, or in other words the chances of occurring or the chances of occurring are of that is equal to each other, the magnitude. Just like I am giving an example very simple all the time, that if you have a coin, so that coin has two faces. So if we see this coin have two microstates, one is head, another is tail. So how many microstates are for the coin? That is 2. And the probability, what will be the probability of the total probability is equal to 1. So we have two phases or two microstates. So if we want to calculate the probability of each phase, so that will be 1 over 2, because we have two phases, that is our two microstates are possible. So the probability for the head will be 50%, and similarly the probability for the tail will be 50% as well, because it's equal to each other magnitude. So similarly if we have other objects that have 4 phases or maybe 6 phases, so correspondingly its probability will be reduces, because the number of the number of phases increase, and correspondingly we can divide that probability in that particular phases, because when the chances of any events increases, so this its probability correspondingly reduces. And that for if we calculate for an object having 6 phases, so we just simply do the calculation by 1 over 6, and that will be the magnitude of probability for that particular case. So this hypothesis that the system is in any one of its accessible microstates. So this postulate is reasonable and does not contradict any law of mechanics that might be quantum or classical, and that can only be confirmed by checking theoretical predictions and comparing those to the experimental observation. So physics is actually an experimental science. Sometimes this postulate is called the fundamental postulate of equilibrium or statistical mechanics. The fourth and the last steps in the statistical description of any microscopic system is the probability calculation. In this step we basically calculate the probability using some assumption or using some calculation, and then we finally end up with the values of that probability for that particular case. So finally we can do some calculation. Once we had the fundamental postulate, we can use that probability theory, and then based on that we can predict their probability or calculate the probability based on some justification. So probability theory is to predict the outcome of experiments, and now we will go through the steps 1, 3, 4 again in detail. So this is something about the statistical description of a system, and very understanding of the system, that how we can statistically describe a systems and how many steps are required for that. In the just like the first step is the specification of a systems, that is macrostate and microstate. The second step is actually the statistical ensemble. I mean we need to know the nature of the particle that is involved in that systems. We also need to know whether the particle are distinguishable or indistinguishable, and correspondingly we can do calculation for that, because if we have a same set of particle and the particles involved in that states are distinguishable, then the possible microstates increases, and when if the particle are indistinguishable, then the set of microstate for that particular systems reduces, because means the number of microstates reduces, and correspondingly the probability will increases. So that is why after specifying the state of a system, understanding the statistical ensemble is also very important. And then we have the basic postulate of probability, and at the end we do probability calculation. So this all work has been done for if we consider any sort of statistical system, just like we have a gas molecules, or maybe the magnetic moment of the ferromagnetic material in ferromagnetic material, magnetic moment and its orientation. So all these 4 steps we need to follow for all the possible systems that is involved in that. So in the next lecture, hopefully we will do some calculation, and we can consider some mechanical problem, and we can apply the 4 steps on that, and finally we can find out the probability for that particular case. So thank you very much for now.